After doing aqueous acid dissociation problems, aqueous base dissociations are pretty much the same thing, so hopefully we can run through this a little more quickly. The first thing I want to mention, and really a key difference for some of these problems, is the idea that when you have a strong base, in many cases, at least an aqueous base like sodium hydroxide, it just dissociates, right? We write the dissociation equation. So for strong bases with group 1 metals, etc. Okay? Highly soluble bases is what we'll say. And I think that's a good enough explanation. So for example, you might have something like sodium hydroxide. So right, NaOH, aqueous. All right, that dissociates. In water, it gives you the species Na plus and OH minus. So it is the raw definition of an Arrhenius base, which it produces hydroxide ions in solution. Okay, and if you needed to write a Kb, I guess I've never written it, but you could write Kb, since it's a base dissociation constant, Na plus over OH minus, and technically I guess it'd be over NaOH, and that would be large. Okay, so it'd be the same basic setup, and I think saying aqueous here kind of implies that water. So if you had any group 1 metal or any super soluble base, that's going to be a strong base. You're not going to put something plus H2O, goes to some stuff. You are going to have a Kb expression, although I've never written one before today, and it's going to be large, right? So if they ask you, if they give you NaOH, it's going to look something like that. So now let's kind of focus on the ones that aren't so straightforward, and they're going to be weaker bases, I guess we should say. So let's start with something like C2H5N. Aqueous. I am declaring this as a base. We're being asked to write base dissociations, so I'll just call it a base. Since this is a dissociation, a base dissociation in aqueous solution, we've got to have our water, and that's a liquid. And what do bases do? Bases accept protons, so it's going to get an H. That's it. So like our acid dissociations gave away an H, and our base dissociations gain an H. Our acid dissociations gave away an H from the end, if possible. Our base dissociations are going to stick an H on the end of the formula, if possible. So there is that symmetry. In this case, we've got our OH minus. In fact, I'll usually do it this way, which is put my conjugate acid here, C2H5N. That's what I had there, but it gained a proton, H plus. It has added an H, and that H has a positive charge. So that's aqueous. Water has donated that proton. It's our acid. And what's left of that water is OH minus. All right? And if we label our conjugate acid-base pairs looking in that direction, this gained a hydrogen to become this. Bases gain hydrogens, gain protons. This lost a proton to become this, so this must have been our acid. You may recall in the previous video, H2O was our base every single time. H2O can do that. It's amphoteric. So as we look at things in the opposite direction, C2H5NH plus turns into C2H5N. Okay? And it does that by losing a proton. So this must be our conjugate acid. And the OH gains a proton to become H2O, and things that gain protons we call bases. And when it's on this side, we call it a conjugate base. All right? Our Kb expression for this is going to be the concentration of C2H5NH plus times the concentration of OH minus over concentration C2H5N. And this has a number. That value happens to be 1.7 times 10 to the minus 9th. And you might note that that's not large. And what I mean by large is the word large, and that's not the word large, so this is a weak base. Okay? So this is a weak base. Okay? So once again, this number, by the way, came from a table. It's not something that I made up. It's not something that you should know. And since it is not the word large, it's a weak base. It's not very good at doing that. In fact, in the equilibrium world, we say this is a reactant-favored equilibrium. Most of the stuff's going to be over here at equilibrium proportionally. All right, let's try another one that might look scary, and it's the dihydrogen phosphate polyatomic ion, Nh2PO4 minus. Okay, that's going to be aqueous. We have been explicitly told that this is an aqueous base dissociation, so that's our base. We are declaring in advance. I have H2O. This, by the way, is amphoteric. We could pull another H off of there, but since this is base, we're going to do it as a base. This is our liquid. You get our conjugate here, H3PO4, which you may recognize as phosphoric acid, so it makes sense that that's a conjugate acid since it's phosphoric acid, and hydroxide, right? This gained in H, that's what bases do to become this. This lost in H, that's what acids do to become this. So I'm forgetting our color coding here. This is our base, this is our acid, this is our conjugate acid, and our conjugate base. Our Kb expression has got to be this stuff, products over reactants to their coefficient powers, H3PO4, OH minus, and H2PO4 minus. And yes, charges matter. This happens to be 1.3 times 10 to the minus 12. And you may note that that doesn't say the word large because it's not, and that means that we again have a weak base. Okay? So there's 3 starting examples, and we'll just toss in a few more here and take care of business. Just like we did the last time, in our base dissociations, we need to add H+, all right? So whatever it is, no matter how scary it looks, you got to add an H+. That's it. And if you add it on the end, if possible. Let's try the hydrogen sulfide ion, HS-. And again, that one's amphoteric, but I'm not worried about that right now. We're just going to work through these examples. So HS-. If we're writing an aqueous base dissociation, or any dissociation, water has to be there. The role of that water is determined by the type of dissociation. This says base. This is going to gain H+. So HS- plus 1H gives you H2S. The minus goes away because it added H+. What's left of the water here is OH-. All right. I'm going to say this is aqueous. H2S is going to be a gas, but whatever. We're going to have a Kb expression, again, because this is a base. We've got H2S, OH-, HS-. And this has a value of 1 times 10 to the minus 7th. All right? It's a weak base. We know that because this is not large. It's not the word large. So this is a weak base. Let's try Ch3 Nh-2. And if you look back at the aqueous acid dissociation equations, this may look kind of familiar. Ch3 Nh-2. This was the conjugate base in one of those examples. We did Ch3 Nh3 plus for one of our acid examples. In fact, as we look here, when this gains a proton, which is what bases do, it's going to become Ch3NH. Now it's a 3, and it's an H+, so we gain a plus there. All right? And then we've got hydroxide left. Once again, in this direction, this gains a proton to become this. This loses a proton to become this. Things that gain protons we call a base, lose protons acid. And in the other direction, conjugate acid, conjugate base, because this loses a proton to become this gains a proton to become this. Base, acid, conjugate base. And you don't have to go base, acid, conjugate base. It doesn't matter. Conjugates are on that side, otherwise the order doesn't matter. Writing our K expression, in this case again, hopefully you're getting the idea that it's the exact same thing every single time, because it is products to their coefficient powers, reactants to their coefficient powers. and this number is a 4.38 10 to the minus 4. And those of you who are familiar with Kas and Kbs, for the CH3 NH3 plus, I had a value that was 10 to the minus 11th, if I recall correctly. And you can calculate that, and that's how I did it, by taking our Kw, the dissociation constant for water, 10 to the minus 14th, and dividing by Kb. All right? The Ka of an acid times the Kb of its conjugate is Kw, and that's something we'll look at in a different video, but good side note. P.S. Weak base, it's not large. All right, two more. We'll go C2H5NH2. Again, if it feels like this is monotonous, it's because it is. It's the exact same thing every single time. Base dissociation, add an H. From water, get something with another H plus, and OH minus. If you're noticing a bunch of compounds here with nitrogens, these are organic compounds known as amines, and that happens to be fairly common in terms of weak bases or bases that are around. I got to add an H plus to this. C2H5NH3 plus. And what's left of the water? OH minus. Our Kb expression, following that same pattern, we got a C2H5NH3 plus, OH minus, and C2H5NH2. And this value is 5.6 times 10 to the minus 4, continuing our theme of these being weak bases. One last example, just so we can feel like we did something exciting. This looks different. In fact, I may not have room to do this, but we'll give it a try. I think this name's right, I'm not too worried. The penta-aqua hydroxo-copper 1 ion. So we've got copper and 5 waters with a hydroxide, and it has a 1 plus charge. Right? So that's actually a copper 2 plus, 5 waters as this complex ion, and the hydroxide. So this would have been hexa-aqua copper 2, but it lost a hydrogen. So as an acid, it would have been that. Anyway, aqueous. This is doing base things, and we have declared that because it says base right there. What do bases do? They gain an H plus. Now, if I gain an H plus here, it doesn't change those. I got a bunch of H2Os. But this OH minus now turns into an H2O, right? And I've added an H plus, so my charge is going to jump again. So I gain a water because the H bonds with that OH. So there's 6 of them now. And my charge goes up by 1 because that is an H plus. So I now have a 2 plus there. And that should be the penta-hydroxy, or penta-aqua copper 2 complex ion. And then hydroxide. Every single time. Our Kb expression for this is this mess, CuH2O6, and that's a 2 plus, OH minus, and Cu with 5 waters, OH, 1 plus for that. And we have a value there of 6.3 times 10 to the minus 8th. If you didn't get the memo, that's another weak base. Okay? So the majority of our strong bases that we're writing out are these super soluble bases like NaOH or whatever. You could have something like NH2 as well, but I don't want to put that into an example here because NH3 is amphoteric, so I want to look at that in a different video. And there we go. Aqueous acid dissociations, take an H off. Which one? Probably the one on the end. Aqueous base dissociations, add an H. Where are you going to put it? Probably on the end. All right. Acids, you're going to make H3O plus. Bases, you're going to make OH minus. And then those are your conjugates.